All right. Let's begin. So just taking stock of where we are, as is our habit. We've been investigating these different equilibrium concepts. And last class we introduced two more. Okay, sort of maybe we gave up on ever being able to find an efficient dynamic that was going to converge to Nash equilibria in every game. And so we thought, okay, why don't we define an even larger equilibrium concept? Okay, and we defined two more last class, correlated equilibria and coarse correlated equilibria. And why did we do that? Well, the hope that we're going to, and the thing that we're going to follow through on this class is that the win that we get by enlarging our idea of what a solution concept is in game theory, of enlarging sort of this concept of what a stable state might be, in this case, by explicitly allowing the correlation of the randomness across different players, that we might actually sort of be able to fulfill this goal of having an efficient learning dynamic, a natural learning dynamic that in any game converges to equilibrium, no matter what the structure is, without assumptions on the structure, without needing to say, well, only if it's a congestion game, or well, only if it's a zero-sum game. Okay, so the goal will be to have like a concrete, efficient learning dynamic that converges to equilibrium in any game. And the caveat is that what we mean by equilibrium is not Nash equilibrium, but correlated equilibrium. Now, if you remember, when we studied convergence of learning dynamics to equilibrium in separable n-player zero-sum games, we sort of took this little detour. We sort of set the game theory aside for a couple of lectures, and we just studied learning. Like, how can you learn to select actions in some difficult adversarial environment in a way that guarantees that you do well according to some natural class of benchmarks. In this case, you do well compared to like the best expert in hindsight. And the reason we did that was because if you've got a learning algorithm like that that can do well according to this benchmark without making any assumptions about where the losses are coming from, for example, it means that this is a learning algorithm that you can deploy in an arbitrary game, in a game where people really are, strategizing. They might really be adversarial, right? Like it might be adversaries in a game. And so, sort of having abstracted away the game theory, we derived this learning algorithm. Then we came back to game theory and we sort of showed, okay, if everyone plays according to this learning algorithm in a separable zero-sum game, we actually do get convergence to equilibrium. So we're going to take the same kind of tact in this lecture. Okay, if you sort of remember, we've defined correlated equilibria now in terms of a notion of regret. Okay, so we're sort of set up to be able to say, if we've got a learning algorithm that can guarantee that no matter what happens, this notion of regret is guaranteed to be small, then we're in business. Then we can sort of immediately say, if everyone plays according to this learning algorithm or anything similar that has the same regret guarantees, then we will have convergence to equilibrium. In this case, correlated equilibrium. So that's the game plan for today. We're going to remind ourselves of our sort of regret-flavored characterization of correlated equilibria. Then we're going to abstract away the game theory, and we're just going to try to design a learning algorithm that has the guarantees that we need. Okay, is that Make sense? Sound like a good plan? Not that there's anything you can do about it at this point, but like to have you on board anyway. Okay. Okay, so in fact, like, sort of like a warm-up, we defined this notion of coarse correlated equilibria, which was even weaker than correlated equilibria, but had the merit that the sort of regret characterization for a coarse correlated equilibrium was in terms of regret to the best fixed action in hindsight. If we have a distribution over play profiles so that nobody has regret to any fixed action, then that distribution is a coarse correlated equilibrium. And that was really convenient because that's already what the polynomial weights algorithm guaranteed. And so we had sort of, as a one-line application of this algorithm, we already developed a quick convergence to this sort of weaker notion of coarse correlated equilibrium. And then, like looking forward to today's lecture, we showed how to describe correlated equilibria in a similar way, but in a way that sort of has more demanding requirements on what regret is. It requires that there's low regret to sort of a larger class of benchmarks. And we don't yet know how to play a game to guarantee that that notion of regret is guaranteed to be small. That's what we do today. Okay, so let's just sort of remind ourselves of what we need to do. So like, first of all, what is a strategy modification rule? A strategy modification rule is just some arbitrary, think about it as like a backseat driver. It's some arbitrary mapping from things you actually did, actions, to things you should have done, okay? Better actions. Okay, and given an action profile, one that specifies how you and everyone else plays, the regret that you have at that action profile to a particular strategy modification rule is just the difference between how well you could have done if you had let the backseat driver go back in time and change your rule, like change your action, like, map what you actually did to what you should have done, assuming everyone else played in exactly the same way. The difference between sort of how well you could have done had that happened and how well you actually did. Okay, so if you could have done better by applying one of these strategy modification rules, you have positive regret to that strategy modification rule. And we gave this sort of definition, this alternative definition of what a correlated equilibrium is. Last class we defined, like an exact correlated equilibrium where this epsilon was 0, but here I'm going to define an epsilon approximate version. And it just says, look, a distribution over action profiles, okay, encoded, if you like, as some signaling device like a traffic light, simultaneously giving you and everyone else suggestions about maybe what they should do. It's a correlated equilibrium if, in expectation, nobody has regret more than epsilon to any strategy modification rule. Okay, so it's like, when the stoplight says green, you're supposed to go. When it says red, you're supposed to stop. When it says yellow, you're supposed to go very slow. But and you could do that, but like you could do other stuff too. Like when it's green, you could stop, and when it's red, you could go, and when it's yellow, you could go very fast, right? Like that would be the result of applying some strategy modification rule, mapping each of your actions to other things you should do. And we're saying, a distribution over suggestions, distribution over action profiles is a correlated equilibrium if you can't do better by doing that or any other strategy modification. Okay. Questions about that? Because we're gonna for the rest of the class, we're gonna like figure out how to like achieve this. So I want to make sure at this point that we don't have confusions about what this means. Yeah. That's right. So just like a, like a mixed strategy Nash equilibrium, like what kind of object is or is not a Nash equilibrium, it's a collection of mixed strategies, one for every player, which in particular define a distribution over action profiles. Here, since we're allowing correlation, like the object itself that either is or is not a correlated equilibrium, like is a distribution over action profiles. Okay, like a stoplight embodies a distribution over action profiles. It's like the uniform distribution over stop go and go stop. Make sense? Can I make it make more sense? Mm-hmm. Because the suggestion might not be deterministic, like, and in particular, the relationship between your suggestion and mine might involve randomness, right? Like, it might be that when the stoplight tells me to go, it tells you to stop only 75% of the time. And that's important for me to understand when I'm like deciding how I should best respond. Okay, so just, just like it can, when we're talking about Nash equilibria, it can be helpful to randomize, like I let you mix between rock, paper, and scissors in rock, paper, scissors. In other situations, it can be too. Good. Other questions? Yeah.
Does the strategy modification for each player change on each iteration, or is it?
It's fixed. It's sort of the definition, right? Like there's no time going on here, right? Like, this distribution is or is not a correlated equilibrium. And the way we tell is we look and we say, is there any strategy modification rule to which you have regret? And if the answer is yes, it's not a correlated equilibrium. And if the answer is no, it is. Good questions all. Others? Okay. Okay, so this is sort of expected regret over a distribution. Now, if you sort of remember back to how we talked about convergence to Nash equilibria in zero-sum games, we started with this, with like the polynomial weights algorithm that is an algorithm for choosing actions over a sequence. So if everyone plays according to this algorithm, what happens is we generate a sequence of action profiles. And then we talked about regret over these sequences and turned those into distributions. In the end, how did we get like a mixed strategy Nash equilibria from a sequence? Well, we turned the sequence into a distribution by just randomizing over the sequence. Okay, so we're gonna do the same thing here. And so I'm gonna like talk about regret now over sequences of action profiles rather than distributions. And since we already did that, I'm gonna have to sort of give more refined names, right? Like when we were talking about the polynomial weights algorithm, we talked about sequences of action profiles that had epsilon regret. Well, that kind of regret, which was just regret to the best fixed action, or equivalently regret to constant strategy modification rules, I'm gonna start calling that external regret. And this new kind of regret, which is sort of regret to arbitrary strategy modification rules, I'm going to start calling this swap regret. Okay, so what does it mean? Today we've got a sequence of action profiles, A1 through AT. We say that the sequence of action profiles has regret epsilon, let's say, if I can point to any player, and I can choose any strategy modification rule for that player. And I find that if I look at the average payoff that player I actually obtained, just like averaged over this sequence, like his actual realized utility over this sequence, I couldn't have improved it by more than epsilon by, like going in and performing surgery on this sequence and applying this strategy modification rule to his action every round. Like if I look on the one hand at how well he actually did on average over the sequence, on the other hand, how well he would have done in this fictional world where everyone else stayed the same, everyone else kept playing exactly the same way, but I applied this strategy modification rule every single day to every action profile in this sequence, that, like the improvement player I could have gotten by doing that is at most epsilon, at most this delta of t, if we say the sequence has regret delta of t. So we, maybe could have gained a little bit, but not much. And this is quantified over all players and over all strategy modification rules. So simultaneously for all players and simultaneously for all strategy modification rules, none of the players could have gained more than this delta of t amount by applying any of the strategy modification rules ex post after the fact. And the reason this is called swap regret is you can think of what a strategy modification rule as doing as swapping out one action for another. Right, like in comparison, this is like a stronger guarantee than what polynomial weights promises. What polynomial weights promises is that you will do, you've done at least as well as the best fixed action in hindsight, saying you wouldn't have done better if you'd played action 1 every single day, or you couldn't have done better if you played action 2 every single day. What this is saying is you could go in and swap out any pair of actions. You could say, okay, well, every time I played action 1, I should have played action 5. And every time I played action 2, I should have played action 12. And you can perform any one of those swaps, even all of those swaps simultaneously. And you can't gain more than a little bit by sort of going and doing that, right? So regret to the best fixed action in hindsight, the thing that polynomial weights promises, this is sort of what you'd get by performing a really coarse, blunt swap, swapping everything out for like action 1, everything out for the same action. But a strategy modification rule can swap each action out for something else, each kind of action out for something else. And what this notion of regret is asking for is that no sequence of swaps like that should gain you more than a little bit in utility. Yeah. No, you're right. All the A's should have superscript T. Yeah, we're summing over the profile, the individual action profiles in this sequence. No, it's a fixed strategy modification rule. So it's still the case, right? Like it's still too much to ask for that you every single day play the best possible action in hindsight for that day, right? So like, again, every question you have can be answered by rock, paper, scissors. Let's go back to rock, paper, scissors. It's too much to ask for that if I'm playing rock, paper, scissors against you, I literally win every single day, right? Like if I get to go back in hindsight and every single day say, okay, well, like today you played paper, so I should have played scissors, and tomorrow you played rock, so I should have played paper, and I got to really like change every single action in a different way. In that case, I could have won every single day, but like obviously there's no hope in sort of designing an algorithm that would do that. So that's not what this is asking for, right? And that the kind of modification of a action sequence that I'd have to engage in to win every single day wouldn't be describable by a strategy modification rule of this sort, exactly because the strategy modification rule the rule can't change from day to day. So this is saying, like, I could consider a strategy modification rule that says, well, whenever you play rock, you should have played paper instead. But I can't consider one that says, well, this time when you played rock, you should have played paper, but this other time when you played rock, you should have played scissors. Like, the strategy modification rule can map rock to scissors, and it can map scissors to paper, but it has to consistently do that throughout the sequence. So this is stronger than what polynomial weights guarantees, but not impossible. Yeah.
What exactly is the difference between swap regret and the external regret?
So external regret is what the polynomial weights algorithm guarantees. And if you like, it is just swap regret, except like we limit the strategy modification rules to just be constant functions, like to just always output rock. Right, so polynomial weights says, you do as well as if you had played rock every day, or you do as well as if you had played scissors every day. This is saying, you can't, that, but also you do as well as if you had, every time you played rock, played scissors instead, and every time you played scissors, played paper instead. Good. Yeah. I think I missed some crucial word. Is the notion of what? Mm-hmm. Each action profile specifies a move for all of the players, right? So like when I'm summing over these action profiles, here I'm changing the action of player I, but leaving the actions of all of the other players fixed. So this action, the sequence of action profiles specifies also actions for the other players, not just player I. Maybe I don't understand the question. So this is just defined as a condition on average utility. It's saying on average, your utility is at least as high as it would have been had you on average done this other thing. Now, you're right, and we will do this in a moment. Like if instead of thinking of this as a sequence, I think of this as a uniform distribution over these action profiles, then my expected utility will be exactly equal to an average, and we're gonna take advantage of that. But right now I'm just defining things for sequences. Okay? Questions? Okay, yeah. So external regret, measured regret to the best fixed action in hindsight. Swap regret is doing the stronger thing. It's measuring regret to this counterfactual in which for every kind of action, like rock or paper or scissors, you can consider a world in which you swapped out every time you played that action for an arbitrary other action. You can sort of perform these swaps separately for each kind of action. Okay. So let me now observe, basically a one-liner, which is what Cole just pointed out, that there's this direct correspondence between averages over sequences and expectations over distributions. And because we have this definition of correlated equilibria in terms of swap regret, in terms of distributions that have no regret or epsilon regret to any strategy modification rule, it is almost immediate that if we have a sequence of action profiles that has regret, swap regret delta of t, the way we've just defined it, then if I think of the distribution that is just the uniform distribution over the t action profiles in this sequence, if I just dump all of the action profiles in this sequence into a hat, and my distribution is just pulling one of them uniformly and randomly out of this hat, well, then this distribution will be a delta of t approximate correlated equilibrium. Okay, and it's almost immediate. It's just, like, what is the definition of a correlated equilibrium? Well, the regret-based definition we gave is that if I sample an action profile from this distribution at random, and then for any strategy modification rule, consider my expected regret to the action profile that I pulled out of the hat and the strategy modification rule, it should be small. But what is my expected regret when my distribution is just, the uniform average over, the uniform distribution over these T action profiles? Well, an expectation, I'll just sum over the support of the distribution, and for every element in the support of the distribution, I'll multiply by its probability, which is just 1 over t here. And I'll look at, okay, what is my regret to that action profile? And I will note that this, my expectation turned into just an average over the sequence. And well, by definition, right, this is just my, this is upper bounded by my swap regret over the sequence. This is just the definition of swap regret over the sequence. And so it's bounded by delta of t. Okay, so there's very little going on in this statement. It's just sort of pointing out that, if I have something that's true about an average over a sequence, and then I just pick a day in that sequence uniformly at random, the average is now an expectation over that random selection. And our definition of swap regret over a sequence is exactly the same thing as our sort of definition of approximate correlated equilibrium over a distribution. We just need that there's no strategy modification rule that can improve over, in one case, the distribution, in the other case, the average payoff over the sequence. Okay, so there's this like direct connection, but like the point is that what we're going to focus on is algorithms that guarantee diminishing swap regret in a sequential prediction setting. So if everyone plays according to these algorithms, what will be generated is a sequence of action profiles that have diminishing swap regret as we've defined it. And the reason we can say that this these algorithms, when played, will converge in any game to correlated equilibrium is this. It's because if we look at just the empirical distribution over play, if indeed the algorithms do what we want and have diminishing swap regret, then the empirical distribution over the play history will converge to an approximate correlated equilibrium. And it's because of this immediate connection. Okay, does that make sense? So the point is now just we're going to focus on sequences, but we shouldn't let that bother us because sequences and distributions are kind of similar. Okay. So now, let's again forget that we know anything about game theory and go back to studying machine learning. Our goal is to design an algorithm that operates in a sequential prediction setting. This is the same setting the polynomial weights algorithm operates in that I'll remind you of on this slide. And design an algorithm that for any sequence of losses that nature or an adversary might throw at us, and crucially, we make no distributional assumptions here because we don't want to make any assumptions that are going to be violated when we start using the algorithm we develop in an adversarial game. We just want to come up with an algorithm that will guarantee that no matter what happens, we have diminishing swap regret. So what's the setting? Well, it's a sequential prediction setting. So again, we're operating in a in a world that has time. There are time will proceed in rounds from little t is 1 to big T. And there's k experts. Again, we're gonna, when we start thinking about using these algorithms to play games, we'll identify the experts with actions. So if you want, you can just think of the experts as actions in a game. And every day, if you're playing this game, you've got to pick one of the actions. Or equivalently, the task of the algorithm is to pick an expert every day. Like that's what it means to use the algorithm to play in a game. Every day it picks an action to play in the game. And then after the algorithm picks an action, well, it learns that every action experienced some loss. In a game, the loss comes from the cost function in the game and the actions of the other players. But since we want an algorithm that would work in any game, we're not going to make any assumptions at all about what that loss looks like. It's just some loss. Every day we learn that, every every action was associated with some cost. Okay, could be arbitrary, and we chose one of the actions. We chose one of the experts. And so the cost experienced by the expert that we chose, that'll also accrue to the algorithm. The algorithm experiences the cost, the loss of the expert that it chose. Okay, and so what we are going to be interested in is the cumulative loss of the algorithm. This will be when you use the algorithm to play a game, the average utility or the average cost of the player who's using this algorithm. It's just the sum over time of the loss of the expert chosen by the algorithm. And what we'd like to promise is that, so far, by the way, right, this is exactly the setup of the polynomial weights algorithm. And the polynomial weights algorithm has the guarantee that no matter what happens for any sequence of losses, the cumulative loss of the algorithm is upper bounded by the cumulative loss of any single one of the experts. The loss of the algorithm is no more than the cumulative loss of expert 1, it's no more than the cumulative loss of expert 2, and so on. Now we're going to ask for something stronger in terms of arbitrary strategy modification rules. What we want is that in the worst case, okay, again, assuming nothing about the sequence of losses, our algorithm should have the promise that the cumulative loss of the algorithm is upper bounded by the cumulative loss of the counterfactual world, in which every day the algorithm, rather than picking action AT, had instead picked action Fi of AT for some strategy modification rule Fi. Okay, so you can, we're just comparing ourselves to this counterfactual world where we let this strategy modification rule be a backseat driver and tell us what we should have done after the fact. And still, we want that, our algorithm should do as well as the best strategy modification rule in hindsight. Maybe not exactly as well. There'll be some delta of t term, but we'd like our algorithm to be such that delta of t is some function that goes to 0 with t. So we can make our regret to any strategy modification rule as low as we want just by playing for long enough. Okay, so this is only a stronger thing to ask for than what the polynomial weights algorithm does, right? The polynomial weights algorithm promises our cumulative loss is no worse than the best fixed expert. Well, that's just instantiated by a strategy modification rule that, like, no matter what, suggests you play rock. Okay, yeah.
Best expert play the same.
That's like the definite, like when we're using the polynomial weights algorithm to play a game, we're sort of identifying the experts with actions. So like rock is one of the experts, and you can think about this as, like he's always whispering in your ear, play rock, right? Paper is an expert. So you could do something more general, right? Like you could say, okay, like I actually have this like heuristic for how you should play rock, paper, scissors that actually looks at the history and suggests different actions. And you could do that. You could run polynomial weights with these different little algorithms as the experts. And then polynomial weights would promise that you do as well as any of these little algorithms. You could do that there, you could do that here. But rather than just asking that we do as well as the best single expert, we're now asking that we do as well as the best sequence of experts that could have been realized by applying a strategy modification rule to the sequence of experts you actually chose. But yeah, it's a good point, actually, conceptually, that we've been thinking about using polynomial weights to play a game in sort of the simplest possible way, just associating actions with experts. But there's no reason you have to do that, right? Like polynomial weights didn't make any assumptions about what the experts were, right? So if you had, 20 different algorithms that you thought might be like good strategies in some game, you could just those could be arbitrarily complicated algorithms themselves. You could instantiate those as experts, and polynomial weights would guarantee that you do as well as the best of them. So you can think, and also more generally for any online algorithm design problem, right? It's not just games. So you can think of what polynomial weights really is as a way of aggregating different decision-making processes of arbitrary sorts. Okay, you can think of it as combining algorithms, promising that your overall utility will be as good as the best of them in hindsight, up to whatever the regret term is. Okay, so that's a good point. Okay, so this is what we want to do. Questions about the goal? Yeah. Yeah. So this is probably some abuse of notation. So what I mean, little o sub t of 1, what does that mean? So what I mean is that the regret bound will be, we prove, will be sort of something that is a function of t. And I want whatever that function to be something that limits to 0 as t gets large. So, it's going to be something like 1 over square root of t in the end. Good question. Other questions? Okay. So how might one do that? Oh, yes. So the expert, like if you had if you had a subroutine that had the ability to read minds and always suggest the right thing, like somehow when it suggests rock, like miraculously, like indeed, like I've played scissors, then the polynomial weights algorithm would let you do as well as that expert. But to run the polynomial weights algorithm, you need access to the suggestions of the expert before the losses are realized. So it might be very hard for you to implement the expert that plays a perfect game because of the mind reading. Okay, but you can think of polynomial weights as a reduction. If you have code to implement any algorithm, given the information that you have at the moment that you sort of need the polynomial weights algorithm to elicit the predictions of the experts, which is before the losses are realized, then the polynomial weights algorithm is like this lightweight wrapper to make calls to these subroutines implementing the experts and do as well as the best of them. And if you have a magic subroutine, the polynomial weights algorithm will do magic stuff. But the magic is coming, the magic's not coming from the polynomial weights algorithm, the magic's coming from the magic subroutine that you brought to the table. Does that make sense?
So if one of the experts was to play something and just by chance it ended up being really good and they won every game, then also would be able to also perform better than that.
Sure. But that's sort of why you sort of expect to see like these log k terms in the regret bound. So suppose, what I'm trying to do is predict the outcome of a fair coin. Maybe my experts themselves are just flipping coins. The chance that my coin matches some other uniformly random coin every time will sort of go down like 1 over 2 to the k. And so if I'm doing this with k experts, I expect this not to happen for any of them as soon as I have played for log k many rounds. And that's sort of some intuition maybe for why the log k shows up in the regret term. If the log k wasn't there, it would imply some impossible things like the ability to by just having my experts flip coins, you know, get the answer right every time for the first log k rounds, because likely, you know, just because I was flipping so many coins, you know, one of them did it. The log k is what makes that impossible thing not be an implication of the polynomial weights guarantee. But it's like tight. Like if it was even a little bit smaller, the impossible thing would be possible. Does that make a little bit of sense? Cool. That was a good question. Other questions? Okay. So how could we possibly do this thing? So just conceptually, you know, say we've played out this interaction for t rounds. You know, what does the strategy modification rule let us do? It lets us say, okay, well, you know, every time you played some particular action j, you should have played some other action. But it doesn't let us disambiguate between different times you played action j, right? Like I can't say like, okay, yesterday when you played rock, you should have played scissors, but today when you played rock, you should have played paper. It has to apply the same modification to any fixed action j. And so it's going to be helpful to think about these sets that I'll define as Sj, which are just all of the days for which you played action j, right? Like you've got these k actions, you played in some interaction for like t rounds, and on some of the days you played action 1, on some of the days you played action 2, so on and so forth. That partitions the set of days. Sj is just the set of days on which you played action j. Okay, so if you've got k actions, you've got S1, S2, S3, all the way up through Sk, right? Just dividing up the days by which action you played on those days. Okay, makes sense. And what a strategy modification rule can do is uniformly change the action you played on any one of these sets of days from, for example, j to something else like j prime. But it can't separately change what you did for different days in the same set. Okay? And so like in particular, right, like a strategy modification rule can sort of say, look, every time you played action j, you should have played action 12 instead. So we can think about what would have happened had you played action 12, the same fixed action every single day in this set of days Sj, the set of days on which you played action j. And so because of that, when we sort of want to bound swap regrets, which corresponds to allowing us to assign a different action for each of these sets, a fixed action for S1, a different fixed action for S2, a different fixed action for S3, like, you know, it should be that any way of assigning actions to these sets doesn't improve. Well, it's sufficient if on no single one of these sets could I have done better by playing any fixed action every day within that set. Okay, a sufficient condition is if I look at my average utility over the days in Sj, my average utility amongst the days in which I played action j, it's enough that I couldn't have improved by more than delta t, again, on average over this set, by instead playing any other fixed action I, right? I can restrict myself to comparing to fixed actions when I'm averaging over this set Sj, because in this set Sj, my actual play was uniform. I actually just played this one action j over and over again within this set Sj. That's how this set Sj is defined. And so a strategy modification rule, you know, its effect within this set has to be constant, right? Like it can say, well, instead of playing action j, you should have played action I. And so if I want no swap regret, it's enough that I have no regret to any fixed action within any of these sets Sj. Okay, because the sets Sj are just carving up space in exactly the same way that a strategy modification rule is forced to carve up space. It can only provide fixed suggestions I on any subset of days for which your actual play J was the same. And so another way of saying this is that we can achieve no swap regret if we can achieve no external regret, no regret to just the best fixed expert simultaneously on each of these sequences Sj. Right? No swap regret is just asking for no external regret separately and simultaneously on each of these subsequences, S1, S2 through Sk. Yeah. We don't, because when we look at our overall swap regret, we will average over these sequences in proportion to how frequently we played them, right? So like what's going to be our overall regret? Well, it'll be my regret on S1 weighted by the size of S1 over T, plus my regret on S2 weighted by the size of S2 over T, plus my regret on S3 weighted by the size of S3 over T. Okay, so like the regret term will be sort of, delta of T plus the size of S1 over T, plus the size of S2 over T, plus the size of S3 over T. And this is a partition of the space. So the size of S1 plus the size of S2 plus the size of S3 is T. So we're just, our overall regret is a weighted average of these regrets, and the weights sum to 1. So if we can promise delta of T external regret on each of these subsequences, we have delta of T swap regret overall. Make sense? Good question. Okay. Yeah, so it's saying we should do as well as the best fixed action. What's the best fixed action? That just means the one that has that minimizes loss. Yeah, so we're minimizing over actions here. Yeah. Oh, no. It better be outside the sum, right? Because this is the difference between like saying you could have done better by playing rock like every single day versus saying you could have done better like on Tuesday by playing rock because your opponent played paper, right? But you're not allowed to make separate decisions every single day. We're sort of committing to a fixed strategy modification rule to apply to the whole sequence.
Just to clarify, it's applying to each, there can be a different I for each set.
Exactly. But within a set Sj, a strategy modification rule can only propose a single action I. Okay. Good questions. More? Okay. So like the best strategy modification rule in hindsight is sort of clear. It's just, for every set Sj, it will swap J out for whatever was the best action in hindsight on that set Sj. Okay, that's what the best strategy modification rule will do. And so sort of like to get some rough intuition about what we're going to try to do, although said this way, it doesn't quite make sense. So we're going to have to figure out how to do it in a way that does make sense. Right, we sort of want to run k copies of polynomial weights, one for each of these sets Sj, because polynomial weights guarantees no external regret. We just need no external regret on each of these k sets Sj, and then we're golden. So why don't we just run one copy of polynomial weights for each Sj, and if on some day T we find ourselves in set Sj, we'll just use the copy of polynomial weights associated with that J. The problem with that is that this is sort of like a self-referential thing. Like I don't know before I choose an action whether today is going to be a member of, set Sj, because the set Sj is the set of all days on which I played action J. Like, until I choose an action, I don't know what set I'm going to be in. So it doesn't really make sense to like upfront say, okay, this is the version of polynomial weights I'm going to run on days for which I play action 1. This is the set of polynomial weights. This is the polynomial weights, copy I'm going to run on days for which I play action 2, because I don't, until I decide on the action, I don't know what I'm going to do. So this is some intuition for why we're going to want to run k copies of polynomial weights. There's sort of k external regret guarantees we want, but we need to solve this like self-reference problem. Okay, so here's a sketch of the algorithm. Maybe let me draw a picture to try to give you some idea of what it looks like. I'll even try to draw it in a place that's visible to the cameras. Although I think on the recordings, the actual video of me is a tiny little postage stamp. So this is mostly a joke. If you're watching online, you're not going to be able to see what I'm drawing, but at least you've got a fighting chance. I mean, you don't have a fighting chance, but you can like try to zoom in. Okay, so we're going to have sort of some like meta algorithm, some algorithm that's sort of like a wrapper. And what it's a wrapper around is k copies of polynomial weights. Okay, polynomial weights 1, polynomial weights 2, polynomial weights k. Okay, sort of, the rough metaphor is we've got 1 copy of polynomial weights for each action. Okay, now ultimately our wrapper algorithm, right, it needs to operate in this expert setting. So it's going to take as input every round, like a loss vector, and it's going to output every round a distribution over experts. Okay, that's the same input-output behavior as the polynomial weights algorithm. That's just the input-output behavior you need to interact in this like online learning setting. Every day, you need to propose a distribution over experts that we will sample from. Right, this is like the mixed strategy you'll play in the game. And then you need to be able to do something with what you've learned about the performance of the experts, which is represented as a loss vector. Now, these copies of polynomial weights that you're running, they think, like, you're sort of running them as simulations in the matrix, but like they think they're living in the real world. So they are expecting exactly the same kind of input-output behavior, right? Like every day, each of these copies of polynomial weights is providing a distribution over experts. Okay, essentially different for each one of them. Let's call it Q. Okay, and is expecting to be fed a vector of losses, 1 for each of the experts, so that it can update its internal state. Okay, and so like in order to even make sense to like run an algorithm like this that you can think of as the algorithms interacting in the real world, it's running like simulations of these other algorithms. They all have to be consistent and believable so that they don't realize they're just simulations. There's 2 things we need to decide upon. First, how do we actually use the distributions proposed by each of these k copies of polynomial weights? Each of the k copies of polynomial weights is proposing that you play some distribution over the experts, but potentially different ones. And we, the algorithm, need to somehow aggregate all of those to play like a particular distribution over the experts in the real world. And then we, the algorithm, learn the actual losses for the k experts in the real world, but we need to figure out what we should report to each copy of polynomial weights. Maybe we should report different losses to each copy of polynomial weights. Okay, and so what this algorithm will do is to the ith copy of polynomial weights, it will report the real vector of losses, but rescaled by pi, the probability that the algorithm plays expert I. So when the algorithm picks an expert according to this distribution P, and it receives this loss vector L, what it feeds back to the first copy of polynomial weights is like P1T times LT. What it feeds back to the second copy of polynomial weights is P2T times LT. What it feeds back to the last copy of polynomial weights is PKT times LT. Okay? Not clear why yet, but that's what it does. Okay, so just to like now go through the pseudocode, we sort of spin up K simulations of polynomial weights, K instances of polynomial weights. Every day, polynomial weights does what it does. In particular, it proposes a mixed strategy, a distribution over the K actions. Okay, potentially a different distribution over the actions for each copy of polynomial weights. We need to aggregate these somehow. In the sketch, it doesn't say how. We'll have to focus on that in a moment. We need to aggregate these K distributions somehow into a single distribution so that we can choose an action. Then, after we play our mixed strategy, we learn what happened. We learn what are the losses for the experts. And our sort of K simulations of polynomial weights, they're expecting to hear what happened too. But we don't tell them exactly what happened. For each copy of polynomial weights, for each copy I of polynomial weights, we tell it what happened. We tell it the loss vector, but scaled down by pi. Okay, so we're now potentially telling something different. We're giving a different loss vector to each copy of polynomial weights because the distribution we played P might put different weight on different experts. Okay? Okay. And so this is like almost a fully specified algorithm, except I haven't yet told you how to combine the different distributions Q into a single distribution P. But is the general framework of the algorithm clear? Yeah.
What is the same, what's different to the W1 through K?
Yeah, so let's see, what did PWs did you say? Oh, polynomial weights. Yeah, so these are just copies of polynomial weights. Initially they're all the same. Initially they maintain like a uniform distribution over the experts. So at day one, they all propose exactly the same thing, the uniform distribution over the experts. But after day one, the symmetry is broken because we are feeding different loss vectors to them after day one. And so polynomial weights updates its mixed strategy, its distribution over the experts as a function of the losses it gets. And so after day one, since we're giving different loss vectors to each of these, all of a sudden these copies of polynomial weights are diverging somehow. They've got different suggestions. And we aggregate those in a way that we haven't yet specified, and then feed back the losses to polynomial weights as a function of our aggregated distribution.
And are the vectors different, like the second round and third round after different because each polynomial weight algorithms are choosing it different?
It's because for two reasons. I mean, it's because, first of all, our algorithm is putting different weights on different experts. Like the P is not going to be uniform. And so, what we feed after round one to the first copy of polynomial weights is like the loss vector, but scaled down by the weight that we put on expert 1, whereas what we feed to the second copy of polynomial weights is the loss vector scaled down by the weight of expert 2, which is different. And as soon as we start feeding them different loss vectors, they start diverging because now the weights maintained by these different copies of polynomial weights are going to be different. Make sense? Cool. Okay. So here's like a little bit of magic that will, the reason for this will become clear as we analyze the algorithm. But like here's how we're gonna aggregate the k different distributions of the k different copies of polynomial weights into a single distribution. So you can think about writing down like a matrix where the first column is the distribution that the first copy of polynomial weights puts over the k experts. The second column is the distribution the second copy of polynomial weights puts over the k experts. Okay, so on and so forth. The last column is the distribution the kth copy of polynomial weights puts over the k experts. This is a square matrix. It's a k by k matrix because each copy of polynomial weights is maintaining a distribution over k experts, and there's k copies of polynomial weights. We are going to take P, our distribution P, to be the top eigenvector of this matrix. Okay, or equivalently, the steady state distribution, if you think about this as a process by which, the first copy of polynomial weights says, okay, well, with probability, like 2/3, you should play action 5, at which point I switch over to the fifth copy of polynomial weights and follow its distribution to another copy of polynomial weights, and I keep doing this forever. This is the steady state distribution of that Markov chain. Okay, if those words don't mean anything to you, don't worry about it. Like we don't need to know, in order to understand what comes next, you don't need to know what a steady state distribution of a Markov chain is. You don't need to know what an eigenvector is. That's fine. But if you do know what those things are, that's where this comes from. That's where this equation comes from. And that's how we know that this is something sensible to ask for. Okay. But if you don't know what those things are, you don't need to. The point is, we have some particular way of aggregating these k distributions, these k sort of proposed mixed strategies for each of these k different copies of polynomial weights into a single distribution, a single mixed strategy. And this way of doing things has the following crucial property that I will tell you now. This is the crucial property of it. You don't need to know what an eigenvector is. You don't need to know what a steady state distribution of a Markov chain is. It's something that you can understand just from staring at this equation. So if we choose experts, if our mixed strategy at the end is going to choose an action according to this distribution P, and we've defined P like this, there are two equivalent ways we can think of our algorithm as choosing experts. Okay, and these two ways of viewing things are going to be important in our analysis. The first is what we're literally doing. Like, literally, the definition of the algorithm is that at every round T, we will choose each expert I with probability PIT. That is how the algorithm is defined. P is the distribution on experts we are choosing. PIT is the probability that we choose expert I. Okay, so that's the first, most straightforward way of viewing what's happening. That's like how the algorithm was defined. But what is PIT? Well, what is the chance we pick expert J? Well, if I just look at this sum, it is suppose I viewed things the other way. Suppose I said, actually what we're going to do is first, we're going to select one of these copies of polynomial weights. And I'm going to select the ith copy of polynomial weights with probability PIT. And then what I'm going to do is I'm going to delegate my decision to the ith copy of polynomial weights. So with probability PIT, I will delegate my decision to the ith copy of polynomial weights, and I will then pick each action with probability proportional to the weight it has in Qi, the distribution maintained by the ith copy of polynomial weights. Okay, so view number one, which is what's actually happening, I choose each expert with probability Pi. View number two, which I claim is equivalent, with probability Pi, I choose the ith copy of polynomial weights, and then I delegate my decision to the ith copy of polynomial weights. And I claim that these two result in exactly the same distribution over choices. And you can understand that by just looking at this. What is the probability I play expert I? Or what's the probability I play some expert J if what I'm doing is picking the ith copy of polynomial weights and delegating my decision to it with probability Pi? Well, there's k different ways I could play expert J. I could have picked the first copy of polynomial weights, which happens with probability P1. And then the first copy of polynomial weights could have played expert J. That happens with probability Q1 of J. Or I could have picked the second copy of polynomial weights, P2. And then the second copy of polynomial weights would have had to play expert J. That happens with probability Q2 of J. Or the third one or the fourth one. And my total probability of playing expert J would just be the sum of all of these terms. For each copy of polynomial weights, the probability that I pick that copy of polynomial weights times the probability that that copy of polynomial weights plays expert J. And so because we've chosen P so that this identity holds, I can equivalently view the algorithm as operating in either of these two ways, either just directly picking expert I with probability Pi, or picking the ith copy of polynomial weights with probability Pi and delegating the decision to that. And it doesn't, I can view the algorithm as doing either of these two things at any moment because they're exactly the same. Okay, so if it's helpful, I can shift my view from one of these to the other. Okay, is that clear? This is the bit of magic in here. Like the rest of it's going to be like a couple lines of algebra. The point is, if we choose our distribution over experts in this particular way, this is how we aggregate the decision, the proposals of these k copies of polynomial weights. Then choosing each expert with probability Pi or delegating my decision to the ith copy of polynomial weights with probability Pi, these are exactly the same algorithm. Okay. Yeah.
It looks like we're finding PJ to see if the form of PIT and by using PIT. What's the difference between PJ and PIT?
Yeah, so it's this sort of a little bit of a, so P is a vector that has k components. Okay, so Pj is the jth component. And I'm saying the jth component of the vector has to satisfy this equality. The right-hand side of this equality has all k components of the vector on the other side. Okay, so like a priori, you might wonder whether it's possible to satisfy this set of equalities. It is, and the reason it is because it's the top eigenvector of a stochastic matrix, and don't worry about it. The upshot of all of that is just that it is possible to satisfy this set of equalities, and in fact, it's not hard to find it. You just have to compute the top eigenvector of a matrix. But once you buy that there is a solution to this, you can forget what an eigenvector is, and you can just, if you buy this fact, then you're good to go for the next slide. Make sense? Okay. So let's finish it up. Remember, we've got these k copies of polynomial weights, and they're kind of like languishing in this simulation, right? They're all like hooked up to the matrix. By the way, I don't know, like, did any of you guys know what the matrix was? Like, I guess it's like this, from your perspective, this old like silent movie that probably came out in black and white, like the 1950s or something. I think of it as like a recent film. Anyways, from the perspective of like the ith copy of polynomial weights, like living in the matrix, right? Like, what it's receiving every day are the vector of losses, scaled down by pi. And what it's playing every day is the mixed strategy defined by its weights, qi. And we can apply the polynomial weights regret guarantee to the sequence of losses it is receiving and the choices that it is making. So what does that guarantee tell us? It tells us something about the cumulative loss of the ith copy of polynomial weights as perceived by the ith copy of polynomial weights. So what is the cumulative loss of the ith copy of polynomial weights? Well, it's just the sum over all, the sum over at round t, it's the sum over all of the actions of the probability that it plays action j times the loss that it perceives if it plays action j, which is the real loss scaled down by pi. Since the loss for every single one of its actions is scaled down by pi, we might as well just pull the pi out. And so the cumulative loss of the ith copy of polynomial weights is just the cumulative loss we would have experienced in the real world had we followed the suggestions of the ith copy of polynomial weights every single day, right? Chosen according to this distribution qi every single day, except scaled down by pi. And what the polynomial weights guarantee tells us is that the ith copy of polynomial weights does as well as the best fixed expert would have done, given the losses it's receiving. Okay, so on the one hand, the cumulative loss of the ith copy of polynomial weights, just this expression here summed up over all of the days, the actual sort of experienced loss of the ith copy of polynomial weights, is upper bounded by the sort of loss of the best fixed expert J star, given what the ith copy of polynomial weights thinks is going on, which is that the loss of the best fixed expert J star is scaled down by pi star. So this is just the polynomial weights theorem we proved, applied to the view of the ith copy of polynomial weights here. So this is true. We have this inequality for each copy of polynomial weights, right? Like we're running k copies of polynomial weights, and each of them has the guarantee we proved a few weeks back. And so the sum over all of the left-hand sides for every copy of polynomial weights will be less than the sum over all of the right-hand sides for every copy of polynomial weights. So let's sum up the left-hand side. Okay, so I'm just taking this expression and I'm summing up over the k copies of polynomial weights. And now, what is this? This is where I want to use our two views of how the algorithm might work. This is the loss that would be experienced by our algorithm if at every day what we did is with probability pi, we selected the ith copy of polynomial weights and then delegated our decision to the ith copy of polynomial weights and played each of the actions j with probability qij. This is just the expected loss of the algorithm if that's how we view it as operating. First, picking a copy of polynomial weights according to this distribution p, and then sampling according to the ith copy of polynomial weights according to qi. But we know that that algorithm is the same as the algorithm that just straightforwardly picks expert j with probability pj. So to this left-hand side, we can actually rewrite it as the loss of the algorithm in this more straightforward view, where we're just summing up overall time, and then we're just picking each expert j with probability pj, in which case we experience loss lj. Right, so when we sum up the left-hand side of this expression over all of the copies of polynomial weights, all we get is the average loss of the algorithm. Okay, and here we've used this sort of two ways of viewing what the algorithm is doing that sort of follows from this weird way we decided to pick this distribution P. Okay, but the upshot is just when I sum up over the left-hand side of this expression over each of my copies of polynomial weights, in the end, I just get the average loss of the algorithm, this thing that I want to bound. What's it bounded by? Well, it's bounded by the sum of the right-hand side, summed up over all of the experts. Okay. Now, remember, for every copy I of the polynomial weights algorithm, the promise is that we do as well as the best fixed expert J star. We do as well as any expert J star. But which expert J star we choose to compare to, well, we can choose a different J star for every copy of the polynomial weights algorithm, because the guarantee of the polynomial weights algorithm, is applied separately to each of these K copies. And so in particular, if we've got some strategy modification rule in mind, for each copy I of the polynomial weights algorithm, we might as well decide that the particular J star that we're going to compare to in this bound up here is f of I. Because we could choose any J star, why not f of I? And so when we do that, and we just sum up over the right-hand side, we get, taking the exact same expression here, but now summing up over the K copies of polynomial weights and instantiating J star for each copy with f of I, we get that the right-hand side is just equal to the expected loss for the sequence of actions that was played after the strategy modification rule was applied. And where our regret term was previously root log k over t, well, we've picked up an extra factor of k, because we just summed up k copies of this regret term. Okay. And so in combination, we get that the loss of our algorithm, no matter what the sequence of loss vectors was, the cumulative loss of our algorithm cannot be any larger than the cumulative loss our algorithm would have experienced had we gone back and applied any strategy modification rule, except by this sort of term that goes to 0 at a rate of 1 over root t. Okay, and now like k root log k over t, over root t. Okay, so summing up, this algorithm, which is efficient, like it's just like we just have to run k copies of the polynomial weights algorithm, this thing promises that no matter what happens for any sequence of losses, it guarantees swap regret, not just regret to the best fixed expert, but swap regret that goes to 0 the longer we play this thing. And so in particular, if we use this to play in a game, that's one way of generating losses. We still have the swap regret guarantee. If everyone else, if all of our opponents also use this algorithm in the game, then they too will have this swap regret guarantee. And when we just see what happens, when we sort of let the game play out, we will inevitably generate a sequence of action profiles that has the no swap regret property. And therefore, the empirical play will converge to correlated equilibrium. Okay, so we now have an efficient learning algorithm such that if people use it, we get convergence to equilibrium, correlated equilibrium in any game. And we have assumed nothing about the game. Okay. And it's like a decentralized dynamic. The players, it's not like you need to like load the game into your supercomputer and like run this thing, right? Like everyone can play this algorithm without knowing anything about the game ahead of time. Like the only thing you need to, just like playing the polynomial weights algorithm, the only thing you need to know to be able to play this algorithm are the actual realized losses for the actions in the game as you play them. You don't need to know sort of what would have happened in different action profiles you've never seen before. Okay. And just sort of solving, right, we know we get to epsilon equilibrium when our regret is less than epsilon. Well, what we find is that we can reach correlated equilibrium, epsilon approximate correlated equilibrium, after a number of time steps that grows now quadratically in the number of actions in the game. Okay, it's a bit worse than coarse correlated equilibria, which grew only logarithmically in the number of actions in the game, but grows quadratically with the number of actions in the game, but is still independent of the number of players. So if the number of actions in the game isn't too enormous, even if the number of players is, we actually get extremely fast convergence to correlated equilibria in arbitrary games. Okay, so not only, you know, as we've expanded out our definition of equilibrium from pure strategy to mixed strategy to correlated equilibria, by the time we get to correlated equilibria, we have a solution concept that is not only guaranteed to exist in all games, but is easy to find. Okay, that's it. I'll see you next class. Don't get COVID.
I think the problem is really that I think we're talking about the like the same as the problem.